Everyone to this session. This talk is about attended over distributed specificity for information extraction in cybersecurity. I am Ehsan Amjadian. I'm the director of AI and technology at DNA RBC. It's a pleasure to have Nicholas Prayogo with me. He's one of our most brilliant machine learning developers. This talk is being co-authored by myself, Nick, if you can go to the next slide, Serena McDonald from Shopify, Dr. Smith from RBC JSOC, and Dr. Abed from Florida Polytechnic University. All right, let's a little bit talk about the team. My team specifically focuses on two areas of artificial intelligence. Well, much more, but a lot of focus on NLP and computer vision. On NLP, we have a lot of work on and a lot of products on understanding structured and unstructured data. An example of it is a cutting edge, deep search engine for structured and unstructured data within organizations. Another example is our state-of-the-art and proprietary building boundary detection algorithm, which is a really hard challenge, and satellite and aerial image processing. Some of the work that we do over there, are world-class problems. Some of them had not been solved previously and before we did, and we're in the process of it's provisionally patented. In the process of finding full patents, but regardless, this is not the main focus of the talk today. The main focus is on information extraction. Let me name a few other areas they work in: recommender engines, graph neural networks, data synthesis, and differential privacy. All right, let's move on to the next slide. So, what is cyber threat discovery, which is the topic of today's talk? The term is really transparent. Automatically gather cyber threat intelligence and locate cyber threats targeting a specific organization out there in the world or in the darkest corners of the internet, some pun intended. It is highly, highly important, especially with the pace of advancements and improvements in cyber threats. More timely discovery of these threats are critical to any organization, especially the ones that hold important assets and important information. All right, with that, let's move on to the next slide. Okay, let me pass the torch over to Nick to talk about some of the dreadful incidents to prime the rest of the talk. All right, Nick, please go ahead.
Beautiful introduction, Ehsan. Thank you so much. So I guess I'm going to scare you all with some scary incidents within the cybersecurity space. But all jokes aside, this really helps put us perspective on how important that cyber threat discovery is, and hopefully leads to a good motivation for our work. So first of all, here a hacker sold U.S. military drone documents on the dark web for just $200. Very, very small price for that. And you can imagine how severe the consequences would be, because these drone documents, so it's just on the the aerospace space. These documents contain highly, highly technical information that can actually affect the country's defense or security. So these documents falling on the wrong hands might actually lead to very, very dire consequences. So on the finance side as well, we can see in about 2014, I believe, yes, 2014, JP Morgan Chase had a really huge hack that affects 76 million households. Might as well just be a whole country at this point. And it was such a severity with this hack that motivates people to actually think of more deeply with their cybersecurity systems and why it's actually important. And then also in the more, I guess, recent crypto space, which has received a lot of hype recently, in 2018, for example, 14 cyber attacks on these exchanges caused a loss of about $882 million. So this is actually a quantifiable attack where we can see how much money is being lost. So yeah, even the crypto space is not safe from these cyber attacks. And the list just goes on and on as well in the aviation industry, for example, over data breaches. So hopefully this shows, I guess, why we're doing cyber threat discovery. We'd like to ensure that we have robust defense mechanisms against such potential threats, even before they occur. So cyber threat discovery, to provide some perspective, cybersecurity measures can be done by via reactive measure or proactive measure. So reactive measures, as you might know, it mostly setting up systems to detect. So the keyword is detect against already known attacks, while preventive measures or proactive measures is mostly doing more hunting or discovering maybe potential threats. And this can be done with cyber threat discovery, where you look at maybe textual documents such as Twitter posts and so on to look for these potential vulnerabilities and perhaps patch your company's or organization's security systems accordingly. So that's the perspective on both categories of cybersecurity measures. And so an example perhaps that might interest you is if a lot of you use Python and using the PyPy library. There's recently a supply chain attack on PyPy. I believe it was as early as August. So as recent as August, sorry. So this attack, it actually, if you've never heard of supply chain attacks, it basically leverages the automatic systems that are in place, whether in companies or even in personal computers, that if you have any CI/CD pipelines that continuously updates itself with the more recent, for example, PyPy libraries, these attacks actually leverage these systems to automatically sneak these malware in. For example, these are the packages there where they're actually malicious. So you can imagine how severe the consequences is. For example, if your company relies on these libraries consistently, and then these malwares suddenly go into, can sneak in through your security systems without you knowing. So perhaps, if you have private repository managers such as Nexus or Artifactory, these private managers, you can maybe, given these news, for example, if you see these news online, then you can parse these articles. Your cyber threat discovery system can parse these articles, extract the more important terms such as these package names, and then you can quickly and more efficiently update your systems accordingly to account for these attacks. So that's, I guess, a neat example of how cyber threat discovery can be done. Obviously, there are more cases where we can use this, but hopefully this kind of serves again as a motivation for this work. Some examples of where this can be applied: Twitter posts, more short form text. Again, even though it's short form, most of these Twitter posts can be ambiguous in nature or unstructured or sparse. A lot of unstructured text over there, which highlights the importance of accurately detecting these cybersecurity terms to discover these vulnerabilities. For example, like this tweet about the latest supply chain risk. Next, you can also look at news articles. Again, can be very these articles can vary in length. Mostly, it's about a page or 2 pages long. And you see, for example, if a cybersecurity analyst were to analyze every single news article out there, it will take a lot of time. And actually, that was what was done in the past. Cybersecurity analysts would manually have to extract the terms themselves to actually understand what are the important terms that are being covered in these news articles to patch the security system. So obviously that would be a very, very lengthy process. Instead, we can maybe help them by automating this procedure. For example, here, I don't really need to, I guess, read the whole article. I can just see, okay, we have a Emotet botnet that is very dangerous malware that actually came up recently, and it's being distributed by this specific Trojan called TrickBot. So TrickBot, Emotet, maybe those are the only important things you need to know to be able to update, patch your security systems. You don't really care about what companies or all these other non-terms in this article. So moving on to the next, which is maybe even longer forms of text, which is cyber threat intelligence reports, or CTIs. So for example, this CTI by FireEye, you can see that these are very detailed documents with very long descriptions, which can definitely help cybersecurity analysts or cybersecurity practitioners to update their security systems. But again, being able to parse, understand these long-form texts quickly and efficiently allows them or the cybersecurity practitioners to quickly update their systems. And if they can quickly read these documents, then they can also read more documents, which means they can account for more threats in a more effective fashion. So yeah, so these are perhaps some examples of how cyber threat discovery can be applied. And with this, we need information extracting techniques, which Ehsan will be covering. So take it away, Ehsan.
Thank you very much, Nick. All right, so we need, as mentioned, information extraction to perform the task of cyber threat discovery, because these discoveries, and even down the road and downstream pipelines, need to be automated. Obviously, this is a labor-intensive and time-consuming task to do manually. So let's talk about some of the areas in information extraction. A well-known one is, which is also used in cyber threat discovery, is NER, name entity resolution, basically finding named entities. Named entities are entities such as location, place, person, organization, so on and so forth. And a next level task in information extraction, which is much relevant to NER, is relationship extraction. So you have the entities, but what sorts of relationships kind of hold between these entities? Is it this person, is it are they a president of such and such company? Do they live in a specific place? So constructing quote unquote knowledge out of those the information that's extracted. Another area of information extraction is ATE, or automatic terminology extraction. The term is very transparent, no pun intended. The idea is to get the terminologies out of a specific document corpus or out there in the world. It's important because it can get you to very, very specific information, and terms and keywords are a measure of specificity. And lastly, is a core reference resolution. If a person has been given some information of, you move on to the rest of the document, they can be referred to in various ways: he, she, they, as pronouns, or the president, as opposed to Barack Obama, for example. And we need to know this. The rest of the information still relates to that person, and think about it in terms of cybersecurity. If that virus is, a critical piece of information is released about it, or malware, or so on and so forth, we need to still detect that this critical piece of information still relates to that same entity. All right, let's move on to the next slide. Now, why ATE? One reason is, well, it's not really explored much in the context of cyber threat discovery. NER, on the other hand, has been extensively explored. No present categories of NER, so basically are required. So basically, with NER, you have a preset list of categories, as I mentioned: location, place. It is very informative, but it also reduces the information reach. So if you have a very specific type of malware, that term, the representation of that term in your distributed representation and your end-to-end deep learning Python can be very informative for your deep learning algorithm to make the optimal decision, would be otherwise entirely missed. And lastly, it's very important for the downstream security operations, as I alluded to. So let's carry on to the next slide. So let's talk a little bit about the advances of ATE in the last, maybe 1 or 2 decades. We have statistical methods methods such as CNC, or C value and C values, methods such as TF-IDF. Anyone have been worked in NLP knows about them. These methods work with frequency ratio. So they look at the relative frequency of of a term relevant to some sort of generic corpus. And that's how they get the specificity out of a term. And there are linguistic approaches, patterns, and templates based on the reasoning behind linguistic patterns, syntactic and thematic structure. And there are hybrid that use both. Each has advantages. Both are super fast. And we introduced in mid 2010s, we introduced distributed representation, which brought deep learning approaches in terminology extraction. This is obviously very, very useful in search engines, in a lot of information retrieval, as well as information extraction tasks. And recently, Nick and I proposed this attended over distributed specificity methods in automatic term extraction that Nick will go over during this talk. All right, so let me pass it over to Nick to talk about some of the literature of cyber threat discovery.
Thanks a lot, Ehsan. Very interesting, definitely, to hear about these advancements in information extraction techniques. So moving on to the cyber threat discovery literature. So again, there's actually not a lot of literature going on here. So I'm just going to provide some work that I've seen in the space, whether it's cyber threat discovery or just cyber threat information extraction, cybersecurity information extraction in general. So one of the earlier papers that we see was this feature-based IOC extraction method, where indicators of compromise. So this is more of a feature engineering based approach. As you can see, this was in 2016, where maybe deep approaches weren't as cool yet, you might know. But here, it's still a very interesting paper. Definitely take a look at this if you're interested. It uses a lot of heuristics to determine what is important and what is not to extract these IOCs. Looking at the grammar, how the words relate to one another, as you can see, the relation checker with the dependency parsers, and using all of these pre-processing and feature engineering techniques to figure out whether a set of words represent a potential compromise and perhaps what kind of compromise it refers to. As I mentioned, they didn't really use much of the deep techniques yet. Instead, they use SVMs for classification. They also use, so in terms of feature engineering, they use a lot of parsing, which has a beautiful suite for parsing these HTML documents that you can find online. But overall, a lot of feature engineering is being done here instead of more end-to-end representation learning that we see more often than not nowadays. So moving on to this paper, the more later paper, we can see that they use BILSTM CRFs for NER in cybersecurity information extraction. So again, as I mentioned, NER is more often used in this space. Perhaps people are more interested in what categories are being used. Here in this case, for example, they have a vendor, application, even hardware types, software types, versions. They're able to classify these categories with this architecture, where the output layer they use a CRF algorithm, which a conditional random field, which makes sure that for example, if normally this software type would be preceded by a specific version or an application type, for instance. So it matters really what the order is to determine what the entities are. So I guess a highlight here is, the paradigm shift that we see from feature engineering to more end-to-end representation learning with neural network-based architectures. And I think you can also see this kind of trend happening in all other fields as well, for computer vision, even reinforcement learning, for example. You used to use more model, feature-based approaches to more deep approaches. Now, more on the recent work that have been done, we can see actually there's one here by Andreas 2020. It's actually it's more of an ATE work, which use semi-supervised model. So they use partially labeled data on Lithuanian cybersecurity terms, and they test this model using multiple. They test this methodology with using multiple models such as LSTMs and GRUs for classification. In terms of the embeddings, they use, I think, fast text as well as BERT. So they experiment all this, and I guess one of the results were that BERT embeddings do help improve the accuracy of these classification. And then finally, we also have data and knowledge-driven NER with attention. We can see that so here it actually leverages the same approaches that you see in this, like similar approaches they use by LSTM-CRF, but instead they also incorporate. So that's more on the unstructured data side, where you feed the data, the deep learning model simply tells you whether it's what kind of entity it belongs to, but it also adds a knowledge component where it incorporates some sort of ontologies or reasoning approaches, where you have more well-known, for example, ways of determining whether something is a hardware or something is a cybersecurity software, for instance. So it kind of combines the symbolic and neural representations of doing NER. So pretty cool implementations of such for cyber threat discovery or cybersecurity information extraction. Feel free to check the papers out, and I guess perhaps this kind of concludes our literature section. Moving on to the next, we're going to just talk about what we did for our study. First, we have the first publicly available dataset known to us, perhaps for English cybersecurity 8. And secondly, we have new architectures for information extraction, I guess for 8 specifically. Third, we have open source our code as well, where you can check it out in the link. Perhaps these slides will be shared after the talk as well. Finally, we have state-of-the-art performance for this data set. Sorry, just a quick detail. I just noticed the date is January 29, 21, but it's actually, so just ignore that. Sorry about that. So
today is November 18th.
November 18, 2021. Yes, just to clarify. Thank you. Sorry about that segue. Cyber 8, so now we're going to talk about our data set. So the one that we created, it was based on malware TextDB, which is a data set for, I believe it's for NER. And we repurposed this data set for just term extraction specifically. So again, to highlight the importance of, the categories might be important, but we want to specifically look at the terms itself. At the time of writing this paper, this data set has about 147 articles. So these are advanced persistent threat articles, APT, with more than 26,000 sentences in like about 1 million words or something. So pretty big data set. And then we label this with zeros and ones for non-terms and terms. And so to do our annotation, we use this term evaluator software that I believe Ehsan and his colleagues worked on during his PhD at Carleton. So it was so we use this software to annotate. We annotate about 2,000.
Correcting over there, my apologies. It was the NLP lab at University of Ottawa.
Ottawa. I'm so sorry about that. Thanks for the correction. So yeah, 2,000 words annotated by the cybersecurity experts. So the reason there's only 2,000 words is because we're doing we're doing a fully supervised setting. So we wanted to label all the data that we can get. So we have a total of 2,000 words, which is upon filtering a lot of the other words. So we only take the words that occur at least more than 30 times in the data set, I think. Pretty small data set, but hopefully this can give some insightful results. As you can see here, we obtained about a 74% agreement score between the experts. So we can see how, so this kind of highlights again the importance of term extraction because of the ambiguity of the task that we're given at hand. So hopefully with this, we can see how our techniques perform on this data set. So now moving on to our the methodology, the basic methodology that we adopt in this case, distributed specificity, which is I guess the first time representation learning or deep learning was used in AT. So this was around 2016. So I like to think of distributed specificity as a combination of local and global representations. So as you can see here at the top, you would see the word-to-vec model that is trained on the local corpus. At the bottom, you can see a glove model trained on the global corpus. And then you can you generate these embeddings using the trained models, one local embeddings and one global embeddings, and then simply concatenate them and then get a distributed representation of this of these words, or sorry, of this particular word. So just for one word, you have local and global representations of this word. Feed it into the classifier, and you get your results with terms and non-terms. So yeah, so that's pretty much the basis around distributed specificity, the concatenation of local and global representations.
Now, let me provide a little bit of context as to where specificity comes from. I did mention it earlier in specificity methods in term extraction and relative frequency. Those are behind a lot of the statistical methods in automatic term extraction and keyword extraction, but they didn't really benefit from the distributed representation that a deep learning offers. So with distributed specificity methods, with this class of methods, we actually do benefit from those. Over to you, Nick.
That's a perfect addition, Ehsan. Thank you so much. So as Ehsan mentioned, these models are highly capable of capturing rich information from these words, but these models, for example, still disregard the non-linear relationships between words, and they often apply equal weight to each word. For example, as we know, cybersecurity terms can be quite broad and vary in forms, in different forms and complexities. There's many, for example, words such as virus or intrusion, or something these can be cybersecurity terms depending on the context in which these words occur. So this is indeed a shortcoming that we need to address. And so how do we tackle this? We use our attended over distributed specificity method, or we shorten ADS. So again, this might not come as a surprise to you. It's a lot of this NLP work being done. We use BERT to more so leverage the attention heads in the encoder blocks, so that we can put more weights into certain words depending on the context, or to give us more richer embeddings with these very large pre-trained models as well. So we take the embeddings with a dimension of 1 by, for example, h for the embedding size. So with these embeddings with BERT, we simply we integrate BERT into our system. So instead of Word2Vec and GloVe in the past, we would have these BERT models here. At the top, you can see our BERT local model. So this is actually a raw, a raw BERT model that it has not been trained. We train it on a local corpus. And then for the global model, we simply use the pre-trained BERT model that has been trained on all these Wikipedia data sets and everything. So the large global model is trained in that regards. And then you combine, again, similarly concatenate the local and global representations you get out of these two BERT models to get a distributed specificity representation. This time it's attended over with these attention-based mechanisms that are inherent in these BERT models. You get the final terms out of this, and hopefully gives better and richer representations and better results. Now, so this previous architecture covers more of the explicit distributed specificity nature, where in another new architecture that we propose, we simply have a more inherent distributed specificity representation. By inherent, I mean we simply use a global BERT model that has been trained on the global corpus, as you can see here, fine-tune it over local corpus, and then this fine-tuning gives us kind of an inherent distributed specificity because the global model gets updated with the local data as well. So, when I say local and global, I'm not sure if I specified earlier, but global means, I guess, the general corpus. Local means the technical corpus that you have. For example, the global corpus can be entire Wikipedia, entire Facebook, Twitter, and then local corpus can be, your specific malware textbooks or any cybersecurity related corpus that you want. So the very specific.
Nick, just adding one word over there, if I may. So maybe more accurately, when you say local, I mean local to cybersecurity. And global would be anything else. And this is a really good way to disambiguate highly ambiguous context. And as Nick put very accurately, they do refer to, at times of training, to the training data related to cybersecurity versus the use of the term or a word outside that context.
Exactly. Yes. Yeah. So beautifully put, Ehsan. I think this way of distributed specificity kind of solves the major issues in the past, where people look at the statistical measures, as you mentioned earlier, where you have the TF-IDF frequencies, and these often can be very hard to distinguish whether a term is a word is specific to this corpus, or it's actually belongs to a more general corpus. So this kind of helps that in that sense. With this, we get an inherent distributed specificity representation, feed it into these classifiers, and we get final terms. So the classifiers, you can use any sort of classifier you want. In this case, we have logistic regression, support vector machines, and MLPs. So moving on to the results, we evaluate our approach with different classifiers. As we can see here, our methods greatly outperform the benchmark, which is thermostat, which is expected because even in Ehsan's previous work, the distributed specificity approach does outperform this benchmark. Then this benchmark was mostly a statistical method benchmark. Now, zooming into the results, we can see that, in general, TADS alone, so this inherent distributed specificity alone without additional global embeddings, outperforms most explicit distributed specificity combination. So it outperforms, word to vector bird, word to vector glove, etc. So it shows that maybe local global representations that are inherently learned upon fine-tuning all over the local or technical corpus might actually be better than explicitly concatenating the local and global vectors. I think also one potential reason is also this the embedding size as well, because if you just simply take from one a TDS model, you might get a more compact representation of these embeddings. Perhaps that's one way we can think about it as well. In terms of the binary classifier, just a quick aside, we still see that MLP is the overall best classifier, because it's again a deep approach, which is in line with Ehsan's previous work as well on distributed specificity. And finally, I guess an interesting insight we see here is that the importance of embeddings is highlighted here, as you can see. With the shallower logistic regression and support vector machines, with better embeddings, we actually get better results compared to the deeper MLP models that we use. So how is this useful? This is useful in case, especially in this case of cyber threat discovery, where these threats can come very quickly, articles published very quickly, and you need to account for this very quickly before these threats harm your own company's systems. Having a fast yet accurate classifier is crucial. So if you can use more of these compact classifiers, you might even deploy a patch even if it's 1 millisecond before the attack occurs. You still save the company from a big trouble. So that's kind of the motivation behind this as well. So inference times are very quick because the embeddings are already pre-trained beforehand. You simply use a classifier during inference. So it should be pretty quick. So just summarizing the observations here, inherent and fine-tuned distributed specificity leads to best performing results, best performing classifiers, better results. Secondly, you can see that the diversity of embedding representations could help improve the classification performance. I'm not sure if I mentioned, but yeah, so if you have TADS and glove, for example, at the top, you can see that it performs better. So perhaps glove helps the TADS model perform better. So maybe some kind of diversity might be needed. But self-attention, and so that's second point. Third point is self-attention perhaps enable simple classification models to perform better while preserving fast inference times, which is very, very important for cyber threat discovery. So just looking at some practical examples here, so feel free to read. So these words over here that we can see. Some common highlights here that we can to highlight some important, I guess, examples. If you see the root, for example, root and, for example, threat. So these words were incorrectly classified by the model is a false negative, but it really depends on the context which these words occur. Similarly, if you look at virus, if you look at manager and archive, these are false positives, even though they could actually be cybersecurity terms. So perhaps the reason for this is we have not feed in the context surrounding the term candidates itself, which is actually the motivation behind our more recent work, which is context-aware ADS. So we weren't actually sure whether to include this in this paper, in this presentation, but we just recently got this paper just recently got accepted to next year's IEEE aerospace conference. So looking forward to you can look forward to checking it out at that conference itself. But basically, some to cover some of the topics, some of the advancements that we did for this application. For the context-aware setting, we built a new data set where for each term candidate, so in the past we only used one occurrence, obviously because we have no context surrounding it. Now we add all occurrences of this word. For example, the word virus, we add maybe 10 or 20 occurrences of virus, each with different context sentences.
So this is Nick. If I may quickly add here, this is to address the issue that Nick just showed. Where you have root and other terms, in our false negative category. So the idea is that hopefully by providing this context architecturally in the deep learning architecture, we can help disambiguate these better. And finding a threat versus not finding a threat can mean saving or loss in, millions, if not more, of, an organizational asset.
Exactly. Yeah. That's a really good point, Ehsan. And even, for example, if you're a cybersecurity analyst reading through these, large, long articles, if you have a model that gives you a lot of false negatives, then you would end up spending more time than you should. If you get a model that gives you a lot of false positive, you end up spending more time than you should. If you get a model that gives you a lot of false negatives, then you end up missing out on a lot of important information. So really important to highlight that, and this is why we're doing this new work. We propose some new architectures here. On the left-hand side, we can see we concatenate. So you have two, for example, archive is the word, and then you have the context surrounding it. We feed it into the BERT model, get these embeddings, so word embeddings and also the context embeddings. We concatenate them, feed it into the MLP model. So pretty simple as that. Second model, the one in the middle, TADS with multi-channel approach. So this was actually inspired by, so feel free to check them out as well. Haiti et al. 2020, where they talk about multi-channel approaches for automatic terminology extraction. You have one, at the top, you have one shared. So I guess I'll start from the bottom. You have the MLP for, so you have the subnetwork for the context embeddings, context words. And you also have a subnetwork for the target word itself that you're trying to predict, for example, virus. And then these two subnetworks takes care of these separately. And also at the top, you have Siamese MLP or any really neural network that has a shared representation of both the word and context embeddings. And then you would simply, after processing, getting outputs from these networks, and maybe you have some the L1 layer to so which is the distance between the word and the context embeddings representation from the Siamese network, concatenate these outputs, and then feed it into your classification layer, and then just backprop accordingly. So this multi-channel approach helps, having separate models, subnetworks to process the word and context embeddings separately. Finally, you have a more advanced version is the TADS, but we also fine-tune our model for classification. So in the past, we would use static embeddings. So this word virus would have the same embeddings no matter what. In this case, the embeddings are updated based on, the classification loss. So these weights are updated, but we don't use all the weights. We simply freeze most of the weights and only use the final layer weights, as you might see in a lot of downstream classification tasks so as you can see in a lot of downstream classification tasks, so that you don't forget, the information that we've learned in the past from perhaps the global corpus, for instance. So these techniques we use for our context-aware setting. I realize I'm short on time, so I'm just going to quickly wrap this up. With the results, we can see that the BERT model end-to-end for embedding generation and classification actually outperforms the rest. As you can see here, so the numbers here you can see 5, 10, 15 is actually the window size. So if I say 5, that means it's 5 context words, 10 context words after and before. So that's, you can see over there. And also if you look at the multi-channel and concatenation method, MC and CC, you can also see they generally outperform the benchmark as well. The performance boost that we can see here is mostly attributed to a recall increase. And recall increase is actually very important. As we discussed earlier, we want to avoid as many false negatives as possible to make sure that, you know, the cybersecurity analysts or the automatic systems that you use to discover your vulnerabilities account for as much but important information as possible. So you don't want to miss out on any important details, as you saw earlier in our examples of how it can be useful. So that concludes our presentation. I think that's all we have for today. Again, this is, as we've talked about the advancements that we've done, this is barely touching the surface on cyber threat discovery. So I guess our objective from this talk is more of to motivate the audience to perhaps do more exploration, research in this cyber threat discovery field, and hopefully come up with even better architectures, better approaches as time goes. So really looking forward to these advancements. Hopefully you've learned something out of this talk. Thank you so much for having me here, and me and Ehsan here. Ehsan, if you have any concluding remarks, please feel free to take it away. Thank you.
Absolutely. Great work presenting, this fascinating topic. Nick, I just want to say at RBC, we really, really value the community that we work in, including this TMLS community. That's why we have, published this work for the cybersecurity community to hopefully take advantage of and even collaborate in. This is a type of technology that does require collaboration across organizations. We have published the data set aside from the previous paper and the new paper that will be published in a few months. If you want a draft of it, ping us. And data sets as well as the algorithm and the code are available for you on GitHub for you to utilize. So with that, I pass it over for questions. Should we just read the questions and answer them, or do we have a moderator? I think let's just read the questions. Let me read them for you, Nick. So how do you determine which weights to use or not use?
So which weights to use or not use, I guess this was asked. Oh, so this was towards the end, I guess, for the...
It was the final architecture.
Final architecture, yes. So perhaps it can be very experimental. You can experiment with, freezing layers up to a certain point. So maybe if you have 12 layers, this is most BERT models, you have 12 layers. You can experiment with, freezing 10 layers. You can experiment with freezing 11 layers, and you can see how the performance changes. But in our case, we simply freeze everything up to the final layer. We just use the final layer for our updated embeddings. So hope that answers your question. Kevin.
So we haven't used a kind of high parameter search over which sets of weights. Presently, we're using the final one as it's the most processed one for now. High parameter search over there would be interesting.
Yes.
So if you want to do this, the code is there. Another question is, could you please share the GitHub link here, which includes the data set? I think, Nick, we can include the GitHub link. I'm not sure how up-to-date the one is, but let's include it here and the dataset link when we get a chance. Perhaps after the talk we will. Yes. Okay.
There's a question on where did you get the data source? From the web crawler or maybe a third-party vendor. So I'm going to attach the data source as well from GitHub. Sorry, one second. apt GitHub.
Yeah. So it was, as mentioned during the talk, and Nick, correct me if I'm wrong, but we did use a public data set for cybersecurity and transformed it to be used for specifically terminology extraction. We have two versions of it. The second version is for the context-aware terminology extraction work, which is the latest one. The previous one was context-free.
So I think there's also a question about building custom web scrapers with frameworks like Scrapey. Actually, yes. So for this experimentation, we didn't actually use that, but perhaps once we decide to use this in our production to turn this into an actual product, correct me if I'm wrong, Ehsan, but perhaps we can use definitely these web scrapers to identify as many cybersecurity articles as possible. So
Yes.
definitely a good point for that. Yes.
Yes, absolutely. So as Nick mentioned, we built the core engine. We received the live stream and the feed, from elsewhere. But yes, we use web scrapers over there and the crawlers to find, all this information in a relatively standardized manner. These are really great questions.
Thank you. Yes, thank you, Krish.
So I don't see any more questions, but maybe passing it over to David if he wants to wrap up.
Yeah, no, I just wanted to say thank you guys. I mean, this is fantastic. It's always a pleasure to have contributions from the team, and it's always a pleasure to have you guys speak. It's a real honor, to be honest. And for those folks that aren't familiar with Ehsan and the work that his team's doing, I don't think it's disingenuous to say he's one of the top NLP practitioners in Canada, and it's like you've done some fantastic work. So if you have an opportunity to work or collaborate, or maybe just reach out and see if it's a good fit to work on the team or with some of these projects, I really strongly hope that you can do that, because like I said, it's a really amazing experience. And I know, Ehsan, you've been a strong pillar in the community, and you've helped out a lot of people sort of wrap their head around some of the work that we're doing, advancements in the field. So anyways, I could sing your praises for a while, but I'll stop there. And I hope folks can connect with you and with Nicholas. It's really awesome to see, get an update on some of the more recent projects that you guys have been doing. So anyways, I just want to say thank you so much. And I know we'll have you on again, but this has been a pleasure.
Really appreciate the opportunity and the kind words, and looking forward to what the community can build out of this. Thank you so much for having us.
Thank you, Nicholas. Thank you, Ehsan.
Right.
And thanks everyone for joining and for all the questions. I think we have a couple minutes, maybe 2 or 3, and then we'll be getting started with the other sessions. So hope to see you in those as well. Thanks all.
Thank you.
Bye, everyone.